The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees.
It's a pleasure to be here this morning at this session. We're talking about Portland-Limestone Cements in combination with the normal supplementary cementing materials that are used in ready-mix concrete. And so why would we do this? The Portland cement industry is under stress because of the pending government legislations, if not federal, then state government legislations in some states and in Canadian provinces, including where I am in Ontario, to put caps on CO2 emissions from point source emissions. And of course, cement plants are point source emissions, and they produce CO2 because of the breakdown of the calcium carbonate rock, the limestone rock, to make cement. So regardless of how efficient they are with their fuel, and most of the cement plants have become very efficient, process efficiency and reducing their energy and emissions from their fuel and production processes, they still have this issue with it that you're making a calcium-based binder. And so you break down calcium carbonate and emit CO2 in the process of making the clinker. So if they can then take some of that raw limestone and intergrind it when they grind the clinker to cement powder and make a technical cement that works, they can reduce their point source emission of CO2 by the amount of clinker they reduce in that mix. So that's where the premise for this thing. This is not a new concept. It's been used in Europe since the 1960s. I think Heidelberg in 65 was the first one to make limestone cements. It's been in the European standards since they've had the combined EN standards. And they have two types of limestone cements. There are Sem2AL, which has up to 20% limestone in it, and they have a Sem2AB, which has up to 35% limestone in it. And it's now the most widely used type of cement. Limestone-containing cements in Europe are now the most widely used cements of all the cements that are being produced in the European countries. So, in Canada, which is the Canadian Standards Association that's equivalent to ASTM in Canada, in 2008 we came up with a new class of cements, Portland-Limestone Cements, distinct from Portland cements. We still have Portland cements, but we developed a new class of Portland-Limestone Cements in our standard, which is A3001, which contains up to 15% blended or underground limestone replacing clinker. Actually, we just got rid of the blended. It has to be underground because that's what the data was based on. Normally, Portland cements contain up to 5% underground limestone. In Canada, they've been doing that since the 80s. ASTM's had it since 2004, I believe. AASHTO M85's allowed it since 2007. So, in addition to reducing the CO2 emissions by putting some of that ground limestone and grinding it in the clinker, when they're grinding the clinker, you also make the limestone deposits that the cement plant's sitting on last longer because you don't have that reduction in the volume when you calcine the limestone. So they can actually increase the life of their quarry somewhat. The other issue that I wanted to make, and I took my slides out, so I was saying it in the bottom points, when properly optimized, the limestone is not inert, which is one of the reasons for the intergrinding, and it contributes to the properties of cement. It acts in two ways. It acts as a nucleation material for accelerating hydration of cement because you're putting fine powders. When you intergrind limestone with clinker, it's much softer than cement clinker, so it gets ground finer. So typically these cements, Portland limestone cements, have about 100 points higher blane fineness to get the clinker at the same fineness it was before, but you've got this increased fineness of the limestone particles. And you also have a wider distribution of limestone particles, therefore you get a number of benefits in terms of shrinkage and finishing properties. In Canada, the Portland limestone cements have to meet exactly the same physical properties as Portland cements. So from a concrete producer's perspective, they shouldn't see the difference. It sets at the same time. It develops one-day strengths and early strengths and late strengths at the same time and the same rate as their straight Portland cement cousins. And our GU cement, the terminology used in 1157, but it's the same as ASTM Type 1, general use cement. So this went in the standard, the cement standard in 2008, then got incorporated into the concrete standard in 2009 to allow the use of Portland limestone cement in concretes. With the exception of sulfate exposures, now, I may or may not get to that depending on timing, but we're addressing that now. And our National Building Code of Canada is being updated now to include references to the Portland limestone cement. So that'll increase its use Right now, largely been doing demonstration projects until it's in the building code. Okay. And this is not to replace supplementary cementing materials. People are either making blended cements or using pozzolans and slag at the ready-mix plant to get special properties, sulfate resistance, low heat, alkali aggregate resistance, etc., increased corrosion resistance. They do that anyway, but we don't want to impact on that. So the idea of Portland-Limestone Cements is they complement this, they don't replace that. So you're not going to trade off fly ash or slag for limestone. It actually increases the replacement of the clinker with the same technical properties, and as I'll hopefully show later, we certainly have a lot of data that shows that the slag and fly ash actually work better with Portland-Limestone Cements than they do with Portland cements, which is interesting. Okay. In the U.S., most of the standards don't allow this, but 1157, the performance spec for cement, does allow, because it doesn't have requirements on the raw materials that go into the cement, just has performance requirements, and at least 2 producers in the U.S. are making cements and have been for a number of years with 10% limestone in them under the spec. And I'll show a few examples at the end of some U.S. uses. And ASTM is looking at changing the 595 blended cement spec in 2011. It's going to be discussed at the December ASTM meeting. It will potentially allow blended cements, including limestone. Mike Thomas and I just finished a report for the PCA summarizing all the data from Canada as documentation to support that ballot item. Okay. So as I said before, the standard says the setting times and strength are the same with Portland limestone cements of the respective types as Portland cements. For moderate heat or low heat cements, it doesn't change anything in terms of the performance requirement, the heat of hydration limits. And as I said, it works very well with slag or fly ash at normal replacement levels. And I mentioned about the nucleation sites. The other thing that happens, you can form carboaluminate hydrates. We're seeing increased carboaluminate hydrates from the reaction of the carbonate fines with aluminate phases in the cement, like the C3A. And when you start adding things like slag and fly ash or metakaolin to the system, which have aluminates, you increase the potential for more carboaluminate formation. And that fills in space and creates strength as well. Okay. We did a lot of concrete data before. We did a lot of cement data initially, and then after reviewing the literature, we did a lot of concrete data. The industry made concrete. Several universities did extensive testing on this before it was adopted in the concrete standard. And of course, one of the big issues, could you use normal pozzolans and slag? And I'll just show a couple of examples, just some concretes. This is one of the company's trials with various water cement ratio concretes. The straight Portland cement is the blue, 10% limestone, 15% limestone. 15 is yellow, pink is 10. And you can just see, even with 0.7 water cement ratio concrete, there's no influence on the strength development performance 1 through 90 days here. And in fact, in some of these mixes, there's a slight enhancement. Sorry, these are in metric units, but you're looking at about 3 or 4 megapascals, 500 extra PSI, even at 1 day, from the limestone cements over the Portland in that case. But again, they're very similar in performance, so you're not seeing a technical change. And if you then take those same cements and mix them with 30% slag, for example, we're actually seeing enhanced performance from, in this case, both limestone mixes are showing enhanced performance over the Portland with slag. In this one mix, we're seeing less of that effect, but still, there's no cases where it's worse than. And in terms of durability issues, just to show some rapid chloride permeability, the ASTM 1202 results, we have a requirement in the Canadian standard for 1,500 coulombs at 56 days for extreme exposures, such as de-icer salt. And these are Portland cements with increasing amounts of limestone here. And here's with 30% slag. And you can say, well, gee, the 15% is not quite as good at 56 days. We wouldn't use 15. We allow 15, but of course with controls, you're looking at 12 to 13% limestone these cements. But at 80 days, 85 days, they've still improved, and they're down below 1,000 coulombs, and you don't see the difference, even those same mixes at 90 days. Okay. So we've done a bunch of trials, and this one was one of them. It was published in the Concrete International back in January, so you may have seen this article. I just thought I'd mention it. Mike Thomas and myself, and this was with Lafarge people. They had 8 concrete slabs 2 years ago, just outside of Ottawa, and 3 to 4 inch slump concrete, 30 MPa, what's that, 4,000? 590 pounds per cubic, 4,500 PSI. and with different amounts of SCM replacements. And they were using a mixed slag, fly ash, SCM in this case, 25, 40, and 50% on top of the limestone, which in this case I think was about 11%. And so what they did is they cast all these slabs at their plant. They were just trying it, and what you see here is rapid chloride permeability results. These are the 28-day results with and without limestone. These are 56 days with and without limestone. The limestone guys are the yellow dots, or those blue dots. So you're seeing the same performance with increasing amounts of SCM replacement of the Portland cement or Portland limestone cement. So we're seeing the same reductions with the pozzolans in this case, regardless of the limestone and regardless of the age. And these are strength results, which of course you can't see. They look like a bunch of bars, but this is the straight cement. This is the limestone cements are in green with different amounts of SCM replacements, and these strengths are going from 3, 7, 28, 56, and then 35-day cores are in the right. These are cores extracted from the site, and of course the core strength was done late in the season. These were done in October, so these cores were extracted early December, and so of course it was cool weather out there, so you wouldn't expect the same curing. But what you see is that they're pretty much identical at all ages. In fact, even the 1 day here with the straight Portland is better than with the Portland limestone is better than the Portland. And as you see, you add SCMs at later ages, the strengths come up even more. We did air void spacing factors on these things, and they're all good. They're all less than 200 microns or 0.008 inches. And they all had a 100% durability factor in the 666 freeze thaw test. Chloride diffusion results are pretty much the same. The big difference, of course, big reductions with the pozzolan replacement levels of the cement. Okay, we did a barrier wall on a highway in cooperation with the Highway Department in Ontario. This is the expressway just going between Niagara Falls and Toronto. It was 3 truckloads of concrete with Portland limestone cement and slag versus straight cement and slag. And we cooperated with the Highway Department and the construction company to get these trials done, and have done testing on it. And so they placed these things. These were it was a light standard transition on a Jersey barrier wall system, and so we did one side was the limestone cement with slag, and this was the other cement with slag. Again, 2.5 to 4 inch slump concrete. These are the data, and I apologize, they're only in MPa here. But the shrinkage, drying shrinkage, was identical. The strengths, even 1 day strengths with the Portland limestone cement and slag, was better marginally. I mean, 0.8 of an MPa, you're looking at 100 psi. So I wouldn't say that's significant. But anyway, there's certainly no reduction in the early age strengths. Freeze thaw durability, 6.6 is identical. This days for salt scaling test is the Highway Department's version of 672, the ASTM test, except that you measure the mass loss. It's identical. And again, the chloride permeabilities are even better with the limestone cement at 28 and 56 days than they were with the straight cement. Just a month ago, we did paving on one of the major highways, expressways across the top of Toronto, where they're widening the pavement. We did 100 meters of paving with limestone cement, again with slag as a binder. And we did a control section on the same lane further down so we could monitor it for scaling resistance and abrasion resistance over the next year or two. It was a 13-foot wide slip-form paving, about 11.5 inches thick, pre-placed dowel baskets. We did some playing around with curing as well. They normally use curing compound. We wanted to look at the moist curing as well. And I don't have a lot of data for this because it's 28 days was actually yesterday, and I haven't got the 28-day data, but I'll show you the 7-day data. Fresh tests we did. We're doing flexure and tensile because it's pavements, shrinkage, freeze thaw, and de-icer tests, chloride permeability, and chloride bulk diffusion, and we did temperature monitoring. And these were done in a premix plant set up for the paving operation, delivered in dump trucks to the site, put into the paving machine, and slip formed out of the paver, just showing here, doing a bull floating, and then here tining, because it was only 1 lane wide, and they didn't use the tining machine, they just did it by hand. And again, Portland limestone cement on the left, straight cement on the right, with 25% slag. It's pretty hard to tell, it looks gray, has tining on it. The orange line divides it, and we've actually marked these so we can go back and find them again. Interesting thing though, in the paving machine itself, this is the Portland limestone cement mix, so it's being augured out to the edge of the slab, and there's very little segregation of the mix. With the normal mix they were using, they were getting some segregation of the fines near the edges of the slab. And you see the dowel basket. So actually the mix was an improved mix in terms of the preventing segregation in the mix with the limestone. And that's something we've noticed on all the jobs. Typically the finishing is easier with the limestone cements because of the increased particle fineness. And this just shows it after the curing compound, and that was our test section with burlap and plastic. And that's just the 7-day data. What we did is we diverted one truck. There were like 18 truckloads of concrete in each section. So we diverted one truck to a lab to get the testing done, so they weren't necessarily identical. The slumps were slightly different in this case. They're looking at about 1-inch slump, 1.5, about 5% air. It was about 65 degrees temperature in the concrete. The weather outside was a bit cooler. The 7-day strength of the limestone mix was lower on this truckload versus that truckload, and the split tensiles sort of reflect that, and the flexurals at 7 days. If this talk was a week later, I'd have the 28-day data. In the U.S., Holcim is producing these 10% limestone cements under 1157 in Colorado and in Utah. They've been used at least 5 state paving contracts, and Tom Van Dam and Al Innes had a talk on this at the Sustainable Pavement Symposium in Sacramento back in September. So I've just got a few slides from them. Again, a lot of these pavements included fly ash. I'm just going to show one example where they used it in Colorado. Due to time, 6.5 miles of concrete pavement, 10% limestone, 20% Class F ash, pretty low water cement ratio for the paver. And they were getting their flexural strengths, and the contractor got a quality incentive based on, I guess, uniformity and quality. And this was done in hot weather, in some cases up to 100 degrees Fahrenheit. And so they were able to do this, and they didn't encounter any problems with the limestone cement. Heidelberg has also, or Lehigh, has been producing limestone cements under the same 1157 spec for a number of years as well. They've done a number of projects. One of them was a silo, 20,000-ton slip-form silo at one of their own operations in Alabama. And they used 40% slag together with the 10% limestone, so they're replacing over half the clinker here. 3 concentric silos using a Type 2 low-alkali clinker, and courtesy of Gary Knight and his colleagues there. That just shows this thing. It's 80-foot diameter and 240 feet high, slip-formed. And there's actually 3 silos, one inside the other. You can see it here. There's 3 rings here. They're all slip-formed independently to make 3 concentric silos. That's the mix design, so you can see that they've replaced a lot of the cement with slag. And then of that 420 pounds of that cement, 10% of that was limestone. And they used a water reducer in a high range for the slip forming. And of course what they're concerned about is strengths for the slipping operation. So they're concerned about their early age strengths as it's leaving the slip form. And so they were looking for about 3,000 psi. Right? Sorry, I just marked 20 mph so it's for the Canadian people to show what 3,000 psi was. That just shows the early strengths that they used as quality control during the slip operation for the 3 different silos. So they were looking at about 5,500 up to 6,000 psi concretes with those kind of mixtures. So, in summary, they have been used successfully in a number of projects, pavements, barrier walls, and I showed a slip-form silo. But there's a lot of other applications they've been using in a lot of precast products. It works well with slag and fly ash at the normal replacement levels that the ready-mix industry is used to using. It's pretty transparent to the users. They shouldn't see a difference, except perhaps in the finishing, because it actually finishes better because of the fines that you have, the extra fines from the limestone. And it allows them to get a 10% reduction in CO2 emissions. So this is something like, although there's all kinds of exotic things, we're going to hear about some really interesting things in the session today. This is something they can do immediately without any impact on performance, pretty much, and affect a 10% improvement in their CO2 emissions. So that's why we're here. Thank you.
Very nice talk, Doug. You said earlier on in your introduction that you, if time allows, you would talk about sulfate resistance, sulfate environment. Could you please comment on that?
Yeah, certainly. When we did our literature review before we adopted this in the Canadian Standard, one of the concerns was there was a lot of conflicting literature on the role of carbonate fines in sulfate resistance, especially at colder temperatures, because of the potential threat of atomicite-type sulfate attack, which occurs at low temperatures in the range of 40 to 50 Fahrenheit seems to be optimum. Standard tests, if you do a ASTM 1012 test at room temperature, you don't see this. So we decided, in the interest of passing this thing and getting a limestone cements in our standard, we'd say not for sulfate resistance at this time. That same restrictions on mineral fillers, like if you're using limestone fillers in the concrete as well. And so what we've done, we've got 3 research programs going, Bob Day at Calgary, Mike Thomas at UNB, and myself, fairly large programs. And what we've done is we've shown that we've actually developed a modified C1012 test that you run at 5 degrees Celsius, which is 40 Fahrenheit, and you take your measurements there, and you can show that if you, at those temperatures, you will form thaumasite. But what we've also shown, with increased limestone, there's an increased risk of thaumasite, but if you mitigate them with the same amount of fly ash or slag you would normally use, you have exactly the same effect. You can prevent the thaumasite from forming. So we think we've got a solution to the potential problem. We've actually amended our cement standard to remove that restriction on sulfate resistance, but that hasn't been adopted in the concrete yet. We've also embarked, I'm just in the middle of casting 50 concretes that we're burying in outdoor exposure to prove the concept in concrete of our mitigation measures with limestone cements. And so that'll be coming over the next few years. But we're pretty confident that this thing will work. So we've actually developed a performance requirement using this modified C1012 test and running them out to 18 months to make everybody feel cozy with the mitigation measures. So that's what we're doing about it. So it's sort of a work in progress, but we're pretty confident that we've got a solution to the potential.
And my second question would be, what's your opinion on if you would see any difference in adding 15% ground limestone, ground calcium carbonate to a concrete compared to this PLC that has 15% already underground?
Well, I didn't get into the purity issues. We have requirements on the purity of the limestone and on contaminants, mainly organics and clay components in the limestone. We meet the same requirements as the European specs for limestone. So if the fillers met the same requirements and they could be dispersed in the mix at similar replacement levels, you'd probably have pretty similar performance. The one thing with the blended cements, the cement companies have found they can drop their gypsum contents a bit and optimize, because you get carboaluminate, so you need less gypsum to control things and optimize. So there are some issues there, but I think that the separate materials certainly have potential as well. But again, it's sort of in progress in terms of the standards, how they deal with that.
Thank you.
You may have partially answered the question, Doug, but I guess what I'm hearing more of, and I was a little bit surprised, is the addition of limestone at the batch plant, where people are putting limestone dust in now, as in quote-unquote SCM. And I have to admit, being a very strong supporter of green technologies, this gives me a little bit of heebie-jeebies due to control factors and other factors. And I was just wondering if you could comment on that.
Well, I understand the issue. I'm not sure how to address that. I mean, certainly with the limestone cement, you know what's in the cement that it comes, and you've got control on that. Now, the ready-mix guy, if they start adding fillers, you can blow your optimum. The reason we picked 15% as opposed to the 20 the Europeans adopted was we found reduced performance when you got up to that level. And so in the order of between 10 and 15 seemed to be optimum in terms of optimizing performance, in terms of not seeing the effect on concrete properties. If you start adding fillers and recycling fillers into the system, the quality of the limestone does impact on the performance. We've seen that from a number of studies in Europe, which is why we included the quality requirements in the limestone. There's all kinds of possibilities out there, but I think one of the things that concerns me in Europe is there's a lot of use of limestone fillers for self-consolidating concrete going into cold foundations, and they just haven't addressed the thaumasite issue there. And I think that's why we're trying to address it up front and try and prevent it from happening before. There's nothing like a failure to stop a product from being adopted in the market.
Thanks very much.